My name is Pranav Sivvam, and thank you very much for attending my talk. I'm going to be talking on abusing stealthy in-memory binary execution techniques in Linux. And yes, a little introduction about myself. I work as an offensive security consultant at AppSeco, and I usually do pen tests on applications, networks, clouds, AWS, ECP, and containers. I also do bug bounty from time to whenever I find the time, and I love playing CTFs. Lock picking is a nice hobby of mine. I still can't open a liver lock though. I can open normal pin tumbler locks, and I like photography. So we're going to be talking about a couple of OPSEC techniques in Linux, and then we're going to do a little bit of malware development and basically building a small dropper. And then I'm going to introduce a small tool that I wrote called Memex. And we're going to be talking about namespaces and some malware that use these techniques. And then some points on detection and how software developers or any blue teams can use. So why is OPSEC important? So the full form of OPSEC is operational security, and it's a process that red teams use to be stealthy, and so that whatever actions they're doing, the blue team doesn't find out. So blue team or EDR, whatever is there on the press. So when you're part of a red team engagement, deployment of tools is necessary. Like, you need to run your code, and you need to it could be for anything. It could be for privilege escalation, it could be for enumeration, or it could be for any post exploitation scenario. And it's inevitable. You have to run some kind of tool or some other thing to bypass some mechanisms, or you want some exploit to run. And when you do this, when you interact with the system, you leave a dot. And you don't want the blue team or whatever EDR, or not EDR, blue team to connect these dots, because if they do, then you're out of the system, they kick you out. And you don't want that to happen. And you also don't want to drop unnecessary files on the system. So it's better if you can load and run these tools from memory without touching the disk. And that's what we're going to be talking about in this talk. So it's Linux. I'm talking about Linux environments, right? Is it that common? Yes, actually it is. 96.3% of the top 1 million web servers actually run on Linux. And the Linux malware samples have increased over 650% from 2021 to 2022. And it's probably doubled now. And there's been a 35, according to a report from CrowdStrike, there's been a 35% year-on-year increase of Linux malware in the wild. And you can see that from this graph. It used to be a lot of Trojans and ransomware before, but now it's just entirely coin miners. And yeah, let's talk about the first thing, memfd create. So memfd create is actually a system call that was introduced in the Linux kernel 3.17. Essentially what it does is it creates a memory inside, it creates a file inside memory, and it uses something called anonymous memory mapping, which means your file or whatever that is created by memfd is called a file descriptor. It isn't backed by any file or device, so you can't actually view it in the file system. It only appears as something under the proc file system. And the reason this system call was introduced in Linux was so, you know how applications talk to each other on the system, right? So this was to mainly help with secure inter-process communication, so that you wouldn't need to have a separate mount point like a tempfs mount point, and you could just create a memfd on the fly. And whatever file that's created in by memfd, it shows up under the /proc/pid/fd directory, and usually it's the number 3. It shows up as a integer number 3, as it's actually a file. This, as you can see, the /proc/2783/fd/3 is actually a file where your memfd is created, and you can execute it using a family of system calls called execv. We'll talk a lot more about that later. So yeah, and this file can't be inspected through the file system. If you try to read it using any general cat command or anything else, you're just going to get garbage data. And once the program or whatever the script that has created this memfd stops executing or terminates, the memfd also disappears and there are no traces left on disk, and so your whatever exploit or whatever malware was running is no longer on disk, and you don't need to do any extra cleanup. And here's the signature of the function. I'm not sure if it's visible, but yeah. So essentially it returns an integer, which is the file descriptor, open file descriptor, and it takes two arguments. The first one is just like a label of the memfd, and the second one is any a flag that specifies how you want to create this memfd. Okay, so let's look at how someone can actually abuse this technique. We have a scenario over here where your red team operator has successfully compromised a server that is running on Linux, and your goal is to execute an ELF. ELF is essentially a binary format in Linux, and it's like your exe in Windows, and so you want to execute an ELF which contains your reversal or any other malware, and you want to do it in memory. We're going to write a dropper, which is basically a script that will fetch your malware from the internet, or just write your malware through the script into your memory. It's basically dropping the malware into your system. So what this dropper is going to do is it's going to create a memfd using memfd create, and then it's going to get an open file object connected to the fd. This is so that we can write to the memory file descriptor, and then we're going to write the elf binary to memory. Then we'll execute the in-memory elf, and yeah, that should give us our reversal. So these are all the steps we want our our dropper to do. So the first thing is, obviously we need to check whether the target is running Linux version greater than 3.17. So we can do that using this uname command. As you can see, it's running a 64-bit architecture, and the kernel version is greater than 3.17. So that checks out. So the first thing is creating a memfd. This is what we want a script to do. So we are doing this in Python. You can do this in obviously a lot more languages. I use Python so that it's easier to explain. So you can there's a function in Python in the OS module called memfd_create, where you essentially just provide the label of the memfd, and then you give a flag, which is os.mfd_close_exec, which basically closes your file descriptor after it's been executed, when it's been executed. And this returns a file descriptor, which is just again an integer. Next thing we want to do, in Python you can't actually directly talk to directly write to a file descriptor. So you want to open the file, you want a file object or file handle to that file descriptor. So we use something called os.fdopen. We specify the file descriptor, and we say we want to write it in binary, because we want to write our ELF, which is a binary, to that memory file descriptor, memfd, which is basically a file. And we get a file object in the response, in the return, as the return value. Next thing, okay, we've opened the file, we've created the memfd, we've got a file handle, now we want to write to it. So for that, what we do is, we take our whatever reverse shell or malware it is. Over here, it's like a small reverse shell that I wrote. I wrote it in Go, but you can do it in anything. Usually people use C or assembly so that your binary is smaller, but just for simplicity purposes, I did it in Golang. It's so you basically you compile the binary, compile the reverse shell, and you get a binary, right? And then you want to create some write statements. You want your script to have some write statements which will take this binary and then write it into the memory file. We can do that by just running this one-liner over here, python 3-c, which will essentially take your file, binary file, break it up into chunks of 32, and spit out some f.write statements, which when executed will write your binary 32 bytes chunk by chunk into the memory file. Okay, now we have our ELF written and we basically have a file ready. Now what's left is executing it. So we can run any exec v family exec v system call, but here I'm going to run os.execv. It will take the location of the file descriptor or whatever executable it is. In our case, it is /proc/ whatever PID it is, and then fd, and then the file descriptor number. And that's where our memfd is. And we're going to take that, and then we take the we specify the name of the executable as hello world. So when it runs, it's going to show that there's some process called hello world running. It's not very stealthy, but just an example. And you can use any execv system call. So another thing is you can also use fexecve, which basically takes your file descriptor as a parameter and instead of the full path. So yes. Okay. Now the next thing is this is our target system. This is our compromise instance, and now we want to run it. We want to fetch the exploit which is running in our the exploit which is on our system, and we want to run it through Python 3 interpreter. So how we can do that is we can just simply host a simple HTTP server on our system, serve our memfd.py, and then fetch it through using curl. Instead of actually saving it onto the system, we can just curl it over the network and pipe it into the Python 3 interpreter. So that's what's happening over here, and these are just some debug statements or extra print statements that are telling what's happening. So you can see first our memfd gets created. We just print out the file descriptor, which is 3, and then that's our PID, and it writes our ELF binary to memory, and it's then executes our binary. Simple. And since our binary was a reverse shell, we can catch it using a netcat reverse shell on our netcat listener on our system, and that's what happens over here. That's our attacker machine, and we get a reverse shell. Then you can simply look at the process tree, and when you do that, you see that our reverse shell or our memfd is running as hello world. So as you remember, that was the name we had given to the executable. Okay. So each process under the /proc that's running in a Linux system has a file called exe, which points to the actual executable that's running as a process. Over here, since we are running a memfd, we are executing a memfd, it points to something that doesn't actually exist on the system. You can see this, right? It's actually point means I'm saying it's a symbolic link. It's a link. This is a link to the actual executable, which is slash memfd something, and that doesn't actually exist on the system. That's not a actual location on Linux, which means it's running via memory. And once this stops executing, this closes, and then the 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 file is no longer accessible. Okay. Um, Hello World is obviously not very stealthy, right? You could easily tell that's not something that should be running, especially on some production servers or something that that needs a lot, that does a lot of processing. You won't expect a Hello World program. In that case, you could use something a little more uh, better, which could blend in with the environment. Something like user libexec GNOME terminal server would make sense, because it's actually a legitimate process in the Linux, in GNOME desktop environment. GNOME is again a desktop environment in Linux. But yes, that helps you blend in a little better, and this is what it shows up in the process tree. Okay, let me just show you a demo. Okay, so the left one is our our compromised session, and that's our attacker session. And I've divided the memfd.py into three sections, three files: load.head, load.tail, and load.bin. And load.head just has the first part, what we've discussed, until the fd open. So load.tail has the remaining end part of the exploit without the f.write statements, because this is because we need to generate the f.write statements on the fly, and I thought this would be easier to demonstrate. And that's two parts of our script. And now we generate the f.write statements. We just write it into load.bin, and this is what load.bin looks like. It's very big. This is because the binary I wrote was probably too big, and that's why I said you could use something like C or assembly to create a smaller binary, which has lesser write statements. And now we just clump all of them together and create one file called memfd.py. Next thing is our file is ready, our exploit is ready, our dropper is ready, and now we're going to serve it over HTTP and start a listener. We're listening on the port 4444. That's what my reverse shell would be sent on. And we start a simple HTTP server using Python. Now this is our compromised instance. Maybe we have a SSH or something, and now we simply curl the exploit over the internet and pipe it through Python 3. And you can see that we've got a connection, which is our reversal. You can confirm that by running the id command. And we take a look at the exe file, and you can see that it points to, it's linked to a non-existent location called /memfd, which indicates that it's running as a memfd file created by memfd create. We take a look at the process tree. and you see that it's running as hello world. That's the name of our process. Sorry, I think the internet just got disconnected. I'm just trying to reconnect. Okay. So, introducing Memex, it's a small tool I've written which essentially automates this process of creating the dropper, and it creates the dropper in either Python or Perl. I intend to add more functionalities in the coming months, but yeah, that's what it does. And it features an option which detects open memfd instances in process. I actually had a demo, but then the file was too big and I couldn't actually transfer it onto this system. So sorry about that. And this is the syntax. Basically, it takes your binary and it takes a language you want your dropper to be in, which could be Python or Perl currently, and then you also give the process name, which is what you saw as hello world, right? You could give something very stealthy, or you could give something like the same thing that I said, gnome libxx server, and it will create a dropper for you. Okay. So what if you're on something like a toaster or something that is running a very outdated version of Linux, less than kernel version 3.17? Uh, then you actually have a different option that you can use called shm_open, which basically creates a shared memory object. Shared memory object is just something that resides in a part of your virtual memory, and yeah, whatever is that is created in as a shared memory object lands up in /dev/shm, but it is not written to disk. So any reboot that you do, after any reboot, it would be wiped. And this actually requires your dev shm to be mounted as tempfs. We'll talk about tempfs next. And this, yeah, it exists until system reboot or until this shm_unlink is called. It's just a function which will unlink your or delete your shared memory object. So that's another option in case you're on a Linux kernel less than 3.17. And coming to tempfs, what is tempfs? It's basically it's a file system in Linux. It's called temporary file system, and it resides in memory. It's very fast also because of this. And essentially anything you create in a tempfs mounted file system will not be persisted across reboots. And usually, I think you might be familiar of /tmp. The /tmp directory is a very is now it's actually tempfs everywhere, but earlier it used to be optional. You could mount it as a tempfs file system or you could not, but now it's everywhere. It is tempfs, and whatever you store on that does not persist across reboots, as I already said. And usually things like sockets or uh, temporary files like that are used for inter-process communication are created and are by software, and they are placed over there. You can just have a look at all your tempfs file systems by running this command. You're just showing all mount points in your system and trying to grep for tempfs. And /dev/shm, it's not used regularly, but it's always mounted as tempfs, whereas /tmp is used more, and it can be tempfs. I say it can because, as I already mentioned, it's optional. It doesn't have to be tempfs. Okay, let's talk about namespaces now. So namespaces are actually a feature in the Linux kernel that let you isolate resources for a set of processes. Resources could be anything like your process name, PID namespace, your mount points, your users or GIDs, or user IDs or group IDs or anything. And this you might be familiar with Docker and Kubernetes. Uh, this is heavily used in such container technologies because you usually in Docker or Kubernetes or in something like LXC you'll have to create um, separate and isolated environments for your other applications or whatever containers you want to run. Okay, we are going to be talking about mount namespace now, and you can create a namespace using something called unshare. It's a command in Linux, and it just creates a new namespace for you. And if you give the -m option, it creates a new mount namespace. And you can use this to isolate your mount points from other processes. So if you create a new mount namespace, whatever mount points you create or you create in this new namespace, they're not going to be visible to other processes. So someone on the same system, suppose blue teamer or a SOC analyst or anyone, could not see your mount points if you create a new mount namespace. Of course, there are different ways to detect that, but then when you want to do something quick and simple, then it's very beneficial. Of course, it needs root privileges, which is again something you have to struggle for. And yes, the namespace is tied to the process created by unshare. And what this means is, when you run unshare, you get a new namespace within the same terminal session. And then if you exit out of that session, then you lose that namespace and anything tied with it is gone. So how can you use unshare and tempfs for stealth, right? By unsharing this mount namespace, a process can have a different set of mounted file systems from other processes. So you could like be on /home or /var and have a separate set of mount points. You could have a tempfs mounted file system, and anyone on the system having a different session would not be able to see that you've created a different mount namespace. And whatever you create in this new mount namespace, right, whatever file that you create, it's not going to be visible to the other set of processes. So yes, this is very useful. As you can see over here, we run the unshare -m command, which creates a new mount namespace, and then we're mounting a tempfs file system on the /loss+found directory. Now the /loss+found directory is very popular in Linux distributions, and this is I just have 5 more minutes, so I'm just going to wrap this up very quickly. So yeah, /loss+found is a very popular popular directory in your Linux distributions, and people don't usually check a lot over there. So what I've done is we're mounting tempfs on loss+found. So anything you create in loss+found is essentially not visible to the other processes or other users who are part of different mount points. So the above screenshot is of our attacker's namespace, and the below one is victims or any analysts. So you can see that when I run the mount command and grep for tempfs file systems, I can only see the /loss+. I can see the /loss+found mounted, but in the other namespace, whoever is investigating, or whoever's just looking through the system, they're not going to be able to look at they can't find your loss+found directory over here because they have a separate set of mount points and they're part of a separate namespace. And this is what happens. So over there, we just let's try to actually download something onto the system and see if it's visible to others. That's what's happening over there. I curl a shell over the network and I save it in that last slash lost plus found directory. You can see it over there, but the other user cannot actually see that in their namespace because their session, because they're part of a different mount namespace. And this is very useful when you want to be stealthy, right? And yeah, I have a demo, but I don't think I have enough time for that. It's essentially the same thing till here. So where has this been used, right? It looks very weird, and I don't know if people have been using it. Right? So there have actually been some malware that employ these techniques. There was something called Panchan, which was a botnet and cryptojacker, and it started showing up around March 2022. It was using Golang's features to maximize its spreadability and things like that. And the sectors it targeted was the telecom sector, the VPS sector, and the education sector. Obviously, in the VPS sector, you must have seen there are a lot of Linux servers, right? And one of the main companies that were targeted was Privex. What this malware was doing was it was just dropping crypto miners as using memfd create. This is just a little more on the malware, but basically it spread by reading the ID, RSA and known host files for other hosts, and that's how it like shifted. And it ran as a process called xinetd, and it basically what it was doing was it was deploying two miners, crypto miners called xmrig and nbhash, and these were being deployed as a memory mapped file using memfd create. And yeah, this was extracted and executed during runtime. And there was another one called secret slib. It actually showed up in the pipi website or pipi repository, the Python repository. And the description was very weird. It was like library that helps with matching and verification of secrets, which doesn't actually make sense. But it was removed very soon also. And not sure why the format, I mean the font shows up like that. That's not how I created it. But yeah, what this thing was doing was it had a bunch of Linux commands as base64 encoded data, which was basically just installing a couple of utilities and then downloading a binary from some server. And what this binary was doing was it was dropping another ELF, a Monero crypto miner, directly into memory using memfd create. Yeah, so basically that's what was happening. And when people saw through, uploaded it on VirusTotal, they were able to see that this was actually being dropped using memfd. As you can see, it doesn't show up in the first or just the direct interface. You actually have to again click on, I think, one of the options over there so that you can see what files were dropped. So detection, I'm almost done. So detection, you need to have visibility into proc. You need to know what of processes are running. You could have better memory scanning capabilities by your whatever AV or EDR it is. And behavior based detection, you don't if you see something that's generating a lot of files or creating a lot of noise, extra unnecessary noise, that's another red flag. And network traffic analysis, obviously you don't want, it's going to look very suspicious, right? If you see something that's sending a lot of HTTP requests or doing a lot of network stuff. So yeah, that was my time. I hope I was able to share or impart some good stuff onto you guys. I hope you understood. And yeah, that's it. Thank you so much.